So we're going to take a step back, okay? We're going to take a step back, and I'm going to show you where some of these relationships come from. So let's assume that we have a composite material, and this material contains fibers. And let's assume for simplicity that all the fibers have the same diameter, okay? Same diameter. And we're going to assume that the fibers are uniformly distributed in the matrix. So we have fibers, and we have matrix, and then the fibers are aligned in the same direction, okay? In this case, we're going to have an object that has a length. It's going to have a thickness, and it's going to have a width. And then we know that all the fibers have the same cross-sectional area, so we know that the area of the fiber is going to be PR squared, where R is the radius of each fiber. And we're going to calculate the volume of the composite by multiplying the width times the thickness times the length. That's going to give us the volume of the whole composite, okay? Yeah. So, hablando de anisotropía, talking about anisotropy, aluminum is, ready? Okay. Okay, let's go back here and we'll come back to anisotropy here in a minute. So we calculate this is the volume of our composite. It's going to be the product of the dimensions, width times thickness and length. And we calculate the volume fraction of the fibers by multiplying the number of fibers, n is the number of fibers, times the length, times the area of each fiber. So this is the area of each fiber, this length is this value, and n is the number of fibers. So this is going to give us the volume fraction of the fibers. So we calculate the volume of the matrix. I'm sorry, this is not volume fraction. This is the volume of the fibers. The volume of the fibers is the volume of each fiber multiplied by the number of fibers. And then the volume of the matrix is going to be the volume of the composite minus the volume of the fibers, okay? So that's what we have. And to simplify the math, we're going to convert this object into this object, okay? So the area of this red parallelepiped is going to be n, which is the number of the fibers, times pi r squared. And then the area of the matrix is going to be the width times the thickness minus the area of the fibers, okay? And we're going to assume that these two objects are perfectly bonded. They're perfectly bonded. So this is a mathematical representation of this. For the purpose of what we want to do, these two objects are equivalent. Now, we define the volume fraction of the fibers as the ratio of the area covered by the fibers divided by the total area, okay? And then the volume of the matrix is going to be equal to 1 minus the volume fraction of the fibers, okay? Now, we're going to go to the laboratory, and we're going to take this object, and we're going to pull it, and we're going to pull it in this direction, okay? And we're going to assume that these two objects are perfectly bonded. They're perfectly bonded. So we're going to grab it, and then we're going to stretch it, and we're going to do this along the length, which is the x direction. And we're going to do this uniformly. So we're going to ignore end effects, okay? So we're going to assume that there are no end effects, and we just take the edges, and then we just pull it uniformly, okay? And these two things are perfectly bonded. So we're going to define the strain in the s direction, and because the two objects are perfectly bonded, the strain of the composite is going to be equal to the strain of the fibers in this direction, and it's going to be equal to the strain of the matrix in this direction, okay? So we grab the ends, pull them, and because they are perfectly bonded, and we are ignoring end effects, the strain in this direction is going to be the same for the fibers and for the matrix. So that's going to be the first equation that we're going to record. The strain of the composite is the same as the strain in the fibers, is the same as the strain in the matrix. And we call this the x direction. Now we're going to make use of our elasticity relationships. We know that the strain is the ratio of the stress divided by Young's modulus. Okay, we're in an elastic regime, everything is elastic. And if we use that relationship, we say that the strain in the fiber is going to be equal to the stress in the fiber divided by the elastic modulus of the fiber. Okay? And the same is true for the matrix. The strain in the matrix is going to be equal to the ratio of the stress in the matrix divided by the elastic modulus in the matrix. Okay? Now, you know that the stress is defined as the ratio of the force by the cross-sectional area. Okay? So we rewrite the strain in the fiber in the x direction as the ratio of the force divided by the product of the area and Young's modulus. And the same is going to be true for the matrix. It's going to be the ratio of the force carried by the matrix divided by the product of the area of the matrix times Young's modulus of the matrix. So because everything is in equilibrium, the force carried by the composite is going to be equal to the sum of the force carried by the fibers plus the sum of the forces carried by the matrix. And if we reorganize those equations, we find that we rewrite this equation. Remember that the forces are the product of the stress times the area. So for the composite, we get this. For the fiber, we get this. For the matrix, we get this. And then we can rewrite the stress of the composite. We take the area and we move it to the other side, so we get these ratios. And if you remember that we had defined the volume fraction of the fiber as the ratio of the area of the fibers times divided by the total area, and the volume fraction of the matrix as the area of the matrix divided by the total area, and knowing that the volume fraction of the fibers plus the volume fraction of the matrix has to be equal to 1, what we get is this relationship, which can also be written in that way, where the stress in the composite in this direction is going to be equal to the stress carried by the fiber multiplied by the volume fraction of the fiber plus the stress carried by the matrix multiplied by the volume fraction of the matrix. Now, going back to our elasticity relationships, you know that the stress is the product of Young's modulus times the strain. So we substitute for the stress here. We substitute for the stress for the fibers. We substitute for the stress in the matrix. If you remember at the very beginning, we had said that the strains were the same. And now we find an expression for the modulus of the composite as a function of the modulus of the fiber and the modulus of the matrix. Okay? This is what we know as the rule of mixtures. Okay? This is the rule of mixtures. So when I show you, when we have that table with the T300 fibers and epoxy, the boron fibers and epoxy, when we calculate those values of elastic modulus, they actually depend on the properties of the fiber and the properties of the matrix. Okay? Which means that if you know the properties of the constituents, you can predict the properties of the composite. And once you know the properties of the composite, you can calculate the stresses or the strains of any structure built with those materials. So this is the procedure by which we can derive the rule of mixtures for a composite where you are applying a load or a stress in this direction. Okay? And something that is very important, this is actually a very important aspect. We made an assumption that these two pieces were perfectly bonded, which means that when we take that composite and we pull it, both the fibers and the matrix are experiencing the same strain. This is what we call the iso-strain condition. And the iso-strain condition is the requirement. This is the iso-strain condition. Is the requirement for the applicability for the rule of mixtures. And this is a very important relationship because if you are dealing with a composite and you know the properties of the reinforcing phase and the properties of the matrix, you can predict what the properties of the composite are going to be using the rule of mixtures, provided you have the iso-strain condition. Okay? So when I show you a table with the properties of a composite, when I show you this table, and you have a composite of fibers, these are the T300 fibers and the epoxy matrix. This value that you see here, you can calculate this using the properties of the fibers and the properties of the matrix using the rule of mixtures. And this is the value that you get. Okay? Now, the modules of the fibers is going to be much greater than 101.81. If you remember earlier this morning, remember that table I showed you with the properties of the fiber? So here are the properties of the single fibers. Okay? You're talking 517 GPa for these high modulus fibers, 295 for the high strength fibers. Compare these values. These are just for the fibers, just for the pure fibers. Okay? Compare those values with the properties for the composite. Okay? So you have 181. So if the modulus of the fiber is 300 GPa, once you make a composite, the modulus is going to be much lower. Okay? And then, as you will see here in a minute, the properties in the direction perpendicular to the fibers are really going to be controlled by the matrix. Okay? So let's see how we calculate those properties. Let's do that little exercise. Okay, so we're going to see this. So this is the rule of mixtures for the iso strain condition where we are applying the stress in this direction. Okay? Questions? No? Okay. Now let's look at this. Let's look at this loading condition. So we have the same object. We have our fibers. We have our matrix. But now we are applying the stress in the perpendicular direction. Okay? So we have the same experiment. We go to the machine, the testing machine in the lab, and now we're going to grab the ends and we're going to pull them. And we are going to assume again that these are perfectly bonded. Okay? These are perfectly bonded. But now we are applying the load in this direction. Here we have the width corresponding to the fibers. This is the width corresponding to the matrix. Again, when you apply the force carried by the matrix is the same as the force carried by the fibers. Okay? If you remember in the previous case, the force carried by the composite was the sum of the forces carried by the fibers and the matrix. Here, the force carried by the matrix is the same as the force carried by the fibers, okay? Which is equal to the force applied to the composite. When you apply this force, you're going to have a change in width. So this is going to stretch, okay? And that's what we call this delta W. The fibers are going to stretch. This is what we call delta W of the fiber. And then the whole composite is going to change width. And this is what we call delta W in the transverse direction, okay? This is the result of applying this force to this composite. So by definition of a strain, the change in width of the fiber is equal to the strain in the fiber in this direction multiplied by the initial width of the fiber. The same is true for the matrix. The change in width of the matrix is equal to the strain in the matrix times the initial width in the matrix. And then if we use our elasticity relationships, we get an expression for the strain multiplied by the initial width. The strain can be replaced by the ratio of the stress divided by Young's modulus. And then the stress can be replaced by the ratio of the force divided by the cross-sectional area. And we can do the same for the matrix. Okay? We can expand these relationships based on the definitions that we just introduced. And then we can calculate the strain of the composite in this direction by this expression, where here you have the force applied to the composite, you have the contribution of the fiber, and then you have the contribution of the matrix. You can play with some algebra. And then you can finally find this relationship for the modulus of the composite in this direction as a function of the modulus of the fiber, the modulus of the matrix, and the volume fraction of the fibers in the matrix. Okay? So when you look at the table that I show you, EX and EY for the composite, this is how they get calculated. If you know the properties of the fiber, and you know the properties of the matrix, and you know the volume fraction of the fibers and the matrix, you can calculate the properties of the composite. So those tables that I show you, with the properties of the composite, that's where they come from. EX, this is the iso strain condition. You use the rule of mixtures to get this value. Okay? When you do this calculation, you have to specify what the volume fraction of the fibers is going to be. So here we have 70% volume fraction of carbon fibers, 50% volume fraction of bottom fibers, 66%, 45%. You know the volume fraction, you know the modulus of the fibers, you know the modulus of the matrix, then you can calculate the elastic modulus in the direction of the fiber, the elastic modulus in the direction perpendicular. You can also calculate the Poisson's ratio. This has to be measured. In this case, this is the shear modulus. You can calculate the specific gravity because you know the density of the fibers in the matrix, you know the volume fractions. So these are the values that you get for the pre-preg, for the composite. Okay? And these are properties for a unidirectional system, just like this. If you know the values for the properties of the constituents and their concentration, then you can predict the properties of the composite. Okay?
Does the properties remain when we are dealing with ceramic composite where the interfaces are weak?
That's a very good question. If you are in the elastic regime, where you have small deformations and the fibers do not debond from the matrix, the answer is yes. If you apply strains beyond the first matrix cracking stress, then everything breaks loose. So all these relationships apply only during the elastic regime where the interfaces are well bonded. In the case of ceramic matrix composites, you know, the interface is relatively weak, but if you apply small deformations, everything's going to stay together. And remember that as engineers, we are never going to design anything beyond either yield for metals or polymers or beyond the matrix cracking stress for composites. So all these relationships will hold for most design applications. If you remember the ceramic matrix composite, the curves look like this, but you're always going to be working here up to the elastic limit. Once you have a crack in the matrix, then everything breaks down. It's really a very complicated process. You have fracture mechanics involved. You have frictional interfaces. I mean, it gets really complicated. So these rules of mixtures apply just during the elastic regime. Okay? Any questions? So the last thing that I want to show you is it really gets more complicated. And I'm giving you in 30 minutes something that probably takes 6 months to go through this. There are courses focused on composite materials. This is what we call classical laminate theory, okay? Where you start building the information from the constituents, and then you start looking at these type of conditions. What happens when you start rotating your fibers? Remember the issue of the fuselage. You know, if everything is nicely aligned in the X direction or the Y direction, everything is very simple. The question is, what happens in real structures where you start having your fibers at 20 degrees, 25 degrees, 45 degrees, 70 degrees? Things get really complicated. So I'm going to go fairly quickly through that. And in this case, just to simplify the analysis, X always corresponds to the direction of the fibers. Y corresponds to to the direction normal to the fibers. And then we're going to introduce another coordinate system. It's going to be the 1-2 system. And this 1-2 system is going to be oriented at an angle theta with respect to the orientation of the fibers. Okay? So when you're analyzing your fuselage type of condition, you say, okay, I'm going to use this coordinate system for my fibers. X is the fiber direction. And then this is going to be changing. As I start winding my fibers in the fuselage and everything starts changing, I'm going to define these angles, and I'm going to refer to those angles as theta. And that's what's going to happen in real structures. There is some nomenclature. Your theta is going to be positive in the counterclockwise, which is this direction. Thetas are positive. You can do the math, but if you start using your references in the opposite direction, your thetas become negative. So these are just some conventions that most people use in the composite structures. And this is an algorithm. This is an algorithm that if you have a material and you want to know, for example, let's assume that you want to know the strains and you know the stresses. And you know how these stresses are applied with respect to how the fibers are aligned. You can calculate the strains by using a series of transformations. And these are linear transformations. So if you took linear algebra and you have a good handle of matrices and multiplying matrices, this is a piece of cake. This is going to be very easy. The first thing that you have to do is you do a transformation for your stresses, where now you look at your stresses in the x or y direction, which is the direction of the fibers or perpendicular to the fibers. You have your elasticity relationships for the fibers. So once you have your axes aligned in the right direction, it's very easy to go from stresses to strains. I just showed you those matrices. And once you have your strains in the direction of the fibers or perpendicular, then you do another rotation, and you go into directions 1 or 2. And that's it. These are just linear transformations. And the only thing that you have to pay attention to is whether you have a positive transformation. In this case, you see how it says plus theta, because we have rotated this angle in this direction to get to x. And then you do a minus theta rotation to go from here to here. And that's it. It's just linear algebra. Once you have your matrices, these matrices is going to be your compliance matrix to go from stresses to strains. And then these are just transformations. This is just what you learn in linear algebra. You're going to have your directional cosines, and then you can rotate, and that will give you. So this is how we calculate the strains from stresses whenever you have some arbitrary angle applied to the composite. So you're an engineer at Boeing, you have your fuselage, and you're playing with this. You have a computer, and the computer is going to be doing all of this for you. And all you have to do is play what-if scenarios. I rotate 20 degrees, are my stresses lower or greater? If I go 90 degrees, I might have some bending, and the bending is really going to kill me, so I got to put more fibers in the zero direction to prevent so much deflection as a result of bending. And that's what happens. This is how these structures get designed. You have many angles. You don't have the same volume of fraction in all the directions. You just have to put the right amount. You still have a material that is anisotropic, but you optimize your structure to survive any arbitrary state of stress or strain. Same thing, this is the opposite problem. You know the strains, you want to know the stresses. Same thing, you rotate to align your strains in the fiber direction, epsilon x, epsilon y. You know how to calculate the stresses from the stiffness matrix. And then once you do your stiffness calculation, you rotate in the opposite direction. It's going to be a negative rotation. And that will get you your stresses in the 1 or 2 direction. And again, everything is being programmed. There are some transformation rules that takes you from the x, y, s system of coordinates to the 1, 2, and 6. And same thing for the strains. You can go from x, y, and z. Remember, this is the fiber direction perpendicular to the fiber direction. And these are some arbitrary orientations, some theta angle. Okay? This is it's very simple transformation on this one. So it's just linear algebra. So give you an example. These are screenshots of software. These are commercially available. This is called the Laminator, where you can build a composite structure. All you have to do is say, I'm going to have 10 layers. My first layer is oriented at 0 degrees, the next one at 10 degrees, the next one at 35 degrees, the next one at 80 degrees. You stack them up as a laminate, and then that laminate can be subjected to any arbitrary strain or stress, and as long as you know what the properties of the material are, you can calculate that. So everything is being now automated, but it's important for you to understand where all these relationships are coming from, okay? You are dealing with anisotropic materials, but the nice thing about this is that everything can be predicted. This is another example of another program called Composite Pro. These are things that people at Boeing or Airbus are using. I mean, if you go and talk to them, they use this piece of software to calculate structures. And a lot of these structures can be interfaced with ANSYS or Abacus if you're using an FEM for a large dynamic analysis and you want to see how the structure behaves. You can make them talk one to the other and do the full calculation. So, any questions? Any questions? I know it's a lot of information, and believe me, there's a whole course. When I was in grad school, it was a 6-month course on composites. So I'm giving you a 45-minute version of that. But I hope you appreciate that. I mean, there's really not a lot of magic. Everything comes from understanding that you have highly anisotropic materials, that the properties of the fibers are really the material that enables these composites. If we didn't have carbon fibers with those spectacular properties, we will not be able to do this. You know, we could probably use steel wires or tungsten wires. You know, tungsten wires are very stiff, but they're very heavy. I mean, the density of tungsten is, I mean, you will never fly an airplane with tungsten wires. You will never fly an airplane with the steel wires. This is where these carbon fibers really come into the picture. They are so light, and they have some tremendous properties that now you can design these incredible structures. They are very anisotropic. So you have all the math as civil engineers, mechanical engineers, just about tensors and vectors. And once you handle that, it's very easy to do calculations for your structures. So, any questions? No? Okay.